We are now getting into a question which is a very important question from the point of view of the seller. How to maximize the revenue earned by this auctioneer? Given that it has one object to sell, how should it sell, according to which price, and what should be the allocation, such that the revenue earned by this mechanism designer is the maximum. So this is also known as the optimal allocation, optimal auction design problem. Now the first question that comes here is that we have to maximize, but maximize with respect to what knowledge of the auctioneer. So in practice, the auctioneer may have a lot of knowledge about the players. The auctioneer might not know the exact type profile, but it may have a belief about what those types can be. So this can come from the previous interaction data. So if an object has been purchased at a certain price, then it knows that roughly this is the type of valuation that people attach to this object. So from that data, we are going to assume that the common prior, the auctioneer knows the common prior distribution over all the types, how different people actually value this object. Now, being this is a probabilistic information, we also have to change the notions of incentive compatibility and individual rationality, make it Bayesian with respect to this common prior. So the Bayesian incentive compatibility we already know. In this context, it is going to be the type set, which is an interval between 0 to bi, and the common prior that we are going to assume is G, which gives a probability distribution over this type profiles. And with this lowercase g, we are going to denote the density of this distribution. Now, by this notation, capital G minus I, S minus I given Si, we are going to denote the conditional distribution over S minus I, given I has observed its type, which is S of I. Similarly, lowercase G minus I will denote the density, and both of this capital G minus I and small g minus I are derived by Bayes' rule from the original distribution. So that is the common prior assumption. So our Bayesian incentive compatibility applies to this setting. Similarly, when we are talking about a mechanism, the mechanism f comma p1 to pn, we can also talk about the expected allocation and the expected payment rule, so which are going to be denoted by alpha and this vector pi. And how is this alpha defined? So alpha I, as before, we had this fi of a specific allocation, so ti minus I. What we are doing in this case is we are taking the expectation. So you can imagine that this ti is the true valuation of player I, while Si is what has been reported. So therefore the allocation decision has to depend only on this lowercase Si, which is what has been reported. And for all the other S minus I's, we are going to take an expectation. So this is the conditional expectation, given that player I's true type is Ti, and it has a belief over this S minus I's, and we are taking the expectation with respect to that. We are taking the integral over all those S minus I's. So note that even though we have used a shorthand for this integral is essentially a multiple integral. So for all S minus I's, there will be one integral, and similarly you can expand this DAS minus I with respect to those valuations of those players. Now, so now this is the expected allocation rule. A player I does not deterministically know what is going to happen, but it has a belief that if it reports Si when its true type is Ti, this is the expected allocation. So this is the probabilistic allocation. Now we should remember that there are two levels of expectation here, because one expectation is with respect to the type itself, because that is also unknown and has a probability distribution over it. The other one is coming from this probabilistic allocation of the original mechanism. So even the object is being allocated in a non-deterministic way. So there is one level of randomization there. The other level is due to the uncertainty in S minus I. So that is the expected allocation. The expected payment is again similarly given by this pi I of small si given t of I. Now that is going to be the payment. So the original payment, if it knew its type and the other's type was also known, then that would have been the payment. But because we are in the Bayesian setting and player I does not have the information about s minus I, then it computes this expected payment, which is also given by the same expectation. So this is an expectation over the original payment. So therefore the expected utility of agent I, we can write that as the TI multiplied by this expected allocation minus the expected payment. Now we know by the definition of Bayesian incentive compatibility that this mechanism is going to be BIC if we have this inequality satisfied. That is, when player's true type is TI and it reports TI, it gets the maximum payoff as compared to any other SI, reporting any other SI. And quite naturally, we'll say that an allocation rule is Bayesian implementable if there exists some payment such that this f comma p is BIC. And in the definition of Bayesian incentive compatibility, what is implicit is the common prior. So whenever we are taking this expectation, we know that this is coming from this G, which is a common knowledge. Now we are going to assume one additional property, which is the independence of the individual distributions, that is the GIs, and then we'll do a characterization of these BIC mechanisms. So this assumption says that suppose these priors are independent, that is agent I's value is drawn from a distribution which is capital GI and with the density of small gi, and this is independent over other agents. So what does it mean? The implication of it will be the joint distribution of all the types of all the players that actually reduces to the product of the marginals. And similarly, because this is independent, when we look at the conditional probability, they are only the products of their marginals, and it is independent of the values of this TI because they are the types are independent. So at some point when we really want to write this alpha of TI given TI, so player I is reporting what their true types are, we will just denote that with this shorthand. This is a little bit overloading of this notation alpha. We will use it to denote it more succinctly. Now the analog of the non-decreasing property in the context of the Meyerson's result that we discussed before, we can define the allocation rule to be non-decreasing in expectation, or NDE for short, if we have this property that this alpha ISI, they are non-decreasing. They are non-decreasing in their arguments. So if SI is smaller than TI, then this inequality should hold. That is, your expected allocation probability will not decrease if your valuation is increasing. Now, one point to note here is that if we have a non-decreasing allocation, which the allocation rule that we have defined in the previous case, that is always going to be non-decreasing in expectation, because since it is true that non-decreasingness was true for all t minus i's, that will always be true even if you take expectations. But in this case, there could be more allocation rules which are non-decreasing in expectation. So this is essentially weakening the idea of non-decreasing. So now comes the result for the characterization of this BIC rules, and it is very similar to what we have seen in the context of DSIC rules. So this is similar to the Meyerson's characterization result. Only difference is that now we are in a Bayesian setting. So we are going to say that a mechanism f comma p is in the independent prior setting is BIC if and only if these two conditions hold. The first condition is that f is non-decreasing in expectation, and this payment formula follows a very similar integral formula. Here also it is now replaced with pi of 0, and the allocations are replaced by the alpha i's, the expected allocation rules. Now we are not going to prove this. Essentially this is you can think of this as the Bayesian version of the earlier theorem, the Meyerson's theorem. The proof can be done in a very similar lines, but we'll just have to take care of the expectations appropriately. So I leave that as an exercise. Now, just to appreciate this result, let us now look at a mechanism where the allocation rule is non-decreasing in expectation, but it is not non-decreasing. So that means that this mechanism is not DSIC, even though it is BIC. So how does the example look like? So let us consider there are only two players here, and each of these players have 5 different types. So the x-axis shows the types of player 1 and y-axis shows the types of player 2. The boxes where 1 is written shows the allocation. The object is allocated to player 1. And for the blank boxes, it is allocated to player 2. So what is the and assuming all the type profiles are equally likely, that is all five types of player 1 occurs with probability 1 by 5, and similarly for player 2. Now we can calculate this alpha 1 of T1. So what is the probability, the allocation probability of player 1? So in the first two types, one can see that as it increases, player 1 has no probability of winning that object. When the type is 3, then it has a probability of 1 by 5 of winning that. In the second, and in the fourth type, it has a probability of winning, which is 2 by 5, and at the end it is 3 by 5. So it is monotonically increasing. For player 2, you see that now we should be counting the blank boxes, that is this 3. So this is 3 by 5 for player 2 winning. Here also it is 3 by 5, here it is 4 by 5, 4 by 5, and finally 1. So here also it is increasing. So even though both these two things, alpha 1 T1 and alpha 2 T2, are monotone increasing, but they are monotone non-decreasing in expectation. While if you look at this f of T1 T2, so for player, let's say for player 1, we can see that it is 1 here for this value of T2, so which is this one. It is increasing at first and then it is decreasing, so it is not monotone non-decreasing. Similarly for player 2 also, if you look at it, there are some cases. So from here to here it dips, so from here to here it increases and then it dips when player 2's type is let's say this is T15. So this is the type of player 1. For both these players, the non-decreasingness is violated, even though it is non-decreasing in expectation. So that shows that with this kind of an allocation rule, you can still have a Bayesian incentive compatible mechanism, but you cannot have a DSIC mechanism. So similar to the incentive compatibility notion in the Bayesian setting, now we can define an analog for the individual rationality. So we are going to call that as interim individual rationality, or IIR. Because this says, so what is the meaning of interim? The player I has observed its own type, which is Ti, but it did not observe the types of the other players. If it was there, then it would have been ex post individually rational. So that says that you take the expected allocation and also the expected payment. That expected utility is always non-negative for all values of Ti. And note that this is only from the point of view of player I. This is you see that the absence of for all T minus I, that was there for the ex post individual rationality, which we defined in the previous case, but that is absent here. Now with these two properties, the Bayesian incentive compatibility and interim individual rationality, we can characterize these two properties using the following lemma, which says that a mechanism is going to be BIC and IIR if and only if these three conditions simultaneously are satisfied. F is non-decreasing in expectation, payment follows this integral formula, and finally the constant of this payment formula is not non-positive. So this is the third condition. And the proof is quite straightforward. We are not going to go into the details. The point is that the first two points here, 1 and 2, we have already seen in the previous characterization result that uniquely determines a BIC mechanism. So the proof essentially requires to show that along with the BIC and IIR, that is along with these first two conditions, 1 and 2 and IIR, that is equivalent to this third condition, 3. Now how can we show the forward direction? The forward direction actually comes directly from the definition of IIR. So all that we really need to do is to apply Ti equal to 0 into this definition. So if we apply Ti equal to 0, then this expression goes away, and this should be greater than equal to 0, which means that pi I 0 must be less than equal to 0. Right? That is the first the forward direction. Now if we apply now to show the reverse direction, we are given that this is true. Then we can write the expression for the utility of player I, the expected utility, which is going to be minus of pi I 0, this expression here, because this term will get cancelled out, because it also has a very similar term that will cancel out, and this is always going to be non-positive, non-negative, and this quantity, the minus of pi I 0, is always non-negative. So therefore together it is going to be non-negative. So it also satisfies the individual rationality, interim individual rationality. So we have shown with this property IIR and 1 and 2 together, which actually is equivalent to BIC, that this 1 and 2 plus IIR is equivalent to 3. So that essentially proves this theorem.